Okay, I'm just going to go through a couple of examples of problems on orbital speed. Um, we talked in class about how if you are in orbit around another body, you have to keep a minimum velocity to stay in that orbit. Otherwise, you're going to fall out of that orbit. So, if you're an object close to the surface, then we use square root of g times r, where r is the radius of the orbit, which a lot of times might be the radius of the planet, maybe Earth, for example. Um, and then g is the acceleration due to gravity. This one's only applicable where g is still valid, right? Okay, the farther away you get from the surface of an object, the more g is going to drop off as you get farther away from that source of gravity. So this one, like I said, it's only applicable if you're close to the surface. The example I did in class on this one was what's the minimum velocity that a space station that's 200 miles above Earth has to maintain in order to stay in orbit. So here's my little drawing. Here's the space station above the Earth. So here's the radius of the Earth, and then the space station's 200 miles above that, and it's in orbit around the Earth. So we could use square root of g times r. The way I got r, I looked up the radius of the Earth. That's 6,370,000 meters. And then I added 200 miles to that to account for this little piece right here. You can convert 200 miles to meters using this conversion factor. Remember these bridge type charts for conversions. I got this number for meters, and so then I add that. I just rounded at this point to 6.7 million meters. And then I take the square root of that times g. And I got about 8,100 meters per second. I converted that. Several people from both classes asked me, how did I get this 18,000 miles per hour? And again, it's just another conversion. You're converting meters per second into miles per hour. So I converted seconds into hours, and then I converted meters into miles, and I got about 18,100 miles per hour, just so we have you know, unfortunately, we work in meters per second in physics, but not in the rest of the regular world. So meters per second doesn't always mean a lot to us, but miles per hour is more, something that we're used to. So anyway, so it has to maintain an orbital speed of 18,100 miles per hour in order to stay in orbit around the Earth. And then the other equation we looked at was if you're like a planet orbiting a star, okay, or something large orbiting something else that's larger. In that case, we have square root of our big G universal gravitational constant times m, where m is the mass of the object that's being orbited, like the star, and r is the radius of the path. The mass of the object that's doing the orbiting doesn't matter. It actually cancels out when this equation gets derived. So with this one, because it uses this gravitational constant g, we would just do factors of change. So I just wrote up a couple of examples of those. One is planet Z has a sun that has a mass that's twice our sun, and the same orbital radius as the Earth. And so I would put that in. I would put 2 in instead of 1 for m. I would put 1 for radius, and I see that the orbital velocity of planet Z is going to be greater than Earth's. it's not direct because of the square root. I mean, it's greater by like a square root of 2 type factor. Another example I did, so then we have planet X. It has a sun with the same mass as ours, but it has half the radius as Earth's orbit. So again, I put that into the same equation using 1 for mass and 1/2 for radius, and that also gives me square root of 2. So if I have a smaller radius, my orbital velocity is going to be greater. And these just are examples of the relationships here. Okay, this orbital speed value has a direct relationship with mass. If mass goes up, the velocity is going to go up. And then it has an inverse relationship with the radius of the orbit. If the radius is larger, then the velocity is going to be smaller. If the radius is smaller, like in this case, then the velocity is going to be larger. And it's not quite a direct relationship because this is a square root. Okay, so anyway, that's just a couple of things on orbital speed so that you have a couple of examples to look at.